Chapter 13 and 12, Heat Transfer by Radiation. Topic 1, Fundamentals of Radiation Heat Transfer. A. Radiation and heat transfer by radiation are two different things. First, radiation itself is electromagnetic waves or photons. It represents the energy emitted by a matter such as fire or the sun. It can travel in the speed of light, which is very fast. Second, heat transfer by radiation is a basic heat transfer mode where the heat is carried by the radiation from a higher temperature body to a lower temperature body. Third, the uniqueness about radiation heat is that radiation heat is constantly emitted by all matters as long as its temperature is greater than 0 Kelvin, no matter whether it is people or furniture. However, due to the low intensity, you may not feel the radiation heat from them. B. Important concept in radiation heat transfer analysis. The first concept is enclosure, as illustrated in these two examples. Enclosure is a closed system or sealed space where there's radiation heat transfer between surfaces. It is required that all radiation calculation must be within the enclosure. Therefore, for some open systems, a virtual surface has to be added to form the enclosure. For example, there's heat transfer flow, radiation heat transfer flow from the cylindrical hull of surface to the large surrounding surface. Since it is open system, a virtual surface area A2 at this temperature and emissivity to represent the surroundings is added to form the enclosure. In the beginning, adding surface to make enclosure might pose a challenge to students. Therefore, please pay attention to how the instructor does it. The second concept is radiation surface, which is surfaces have the same temperature. For example, for this cylindrical enclosure, there are three physical surfaces: the top, the bottom, and the side. Since the bottom and the side surfaces have the same temperature, they are counted as one radiation surface. As a result, the total number of radiation surfaces for this enclosure N is 2. The last concept is about enclosure surfaces, which can be blackbody surface or gray surface. If the surface has emissivity over 1, it is a blackbody surface. Otherwise, it is a gray surface. C. New radiation heat rate equation. In the past, we introduced the equation 1 to calculate the heat rate, radiation heat rate between a solid small surface and a large surrounding surface. A new equation 2 has to be introduced to calculate the radiation heat rate between two surfaces at a different temperature where their surface area are close to each other. We checked this new equation and noticed that only the f12 is a new variable, which is a view factor. Topic 2, view factor. A. Define view factor. First, let's look at example of a 3-surface enclosure with the surface 1 of the sun and the surface 2 of the earth and the surface 3 of the deep space. If all radiation heat leaving surface 1 of the sun toward all direction is 100 watt, only 1 watt is received by the surface 2 of the earth. The ratio between these two radiation heat rate is our view factor F between surface 1 and surface 2. Second, we can define a general form for view factor F between surface I and surface J, which is radiation heat received by surface J over all the radiation heat leaving surface I. Third, the view factor value ranges between 0 and 1. B. View factor calculation. Why do I care? This is because view factor plays the same role in radiation calculation as the heat transfer coefficient in convection calculation. We have to know the view factor value to get the radiation heat rate value. But how? There are 3 methods. The first method is to use the view factor equation in the tables based upon the geometry and the orientations between surfaces. The second method is to get view factor value by directly reading the figures. Now let's use example 13-1 to show how to find a view factor by using table and figure. First, there is a coaxial parallel discs at a different temperature Ti and Tj. Therefore, there is a radiation heat flow. That's the reason we're interested in finding view factor F between surface I and surface J. We know the radius for both discs and the distance between them. Second, we go to table 13.2 to select the view factor equation because they have a similar geometry and the orientation between surfaces. Third, we plug into numbers for Ri, Rj, and S, then into view factor Fij to get its value. Fourth, we read figure 13.5 to get a view factor for this coaxial parallel discs. The vertical axis represents view factor. The horizontal axis represents the ratio L over Ri. For our case, it is 2. Those solid red lines represent how the view factor changes with the ratio of I over Ri for different value of Rj over L. For our case, the ratio is 0.3, which represent this solid line. Next, we start with 2, go straight up, intersect with the line of 0.3, then go straight to the left. Finally, we can read the view factor value. B4. The concept of a 2D and a 3D geometry of an enclosure. The reason we come back to table 13.1 and 13.2 is that there's a question raised, which is, if you look at this enclosure geometries, they're all three-dimensional. How come we have a two-dimensional geometry? Here is a definition. If a surface area is so small, like this two and the surfaces, their contribution to the radiation exchange between the three large surfaces can be neglected. Therefore, this 3D geometry of enclosure becomes a 2D geometry of enclosure. Similarly, this is a 3D geometry of enclosure. This is 2D geometry of enclosure, because we only care about the radiation exchange between the top surface and the bottom surface due to neglected small side surface. Generally speaking, if the area is 10 times smaller, its contribution to the radiation heat exchange can be neglected. B5. The third method is to get view factor value by using the rules that view factor follows. The first rule is reciprocity rule for any two surfaces I and J. It is represented in equation 1. For example, for this three-surface enclosure, the surface area A1 times view factor F12 equals surface area A2 times view factor F21. The second is a summation rule for enclosure only. It is represented in equation 2, where N is the total number of radiation surface for an enclosure. For example, for this three-surface enclosure, the total number of radiation surface N is 3. We let I equal 1, which we focus upon surface 1. The summation rule states that I equal 1, J changes from 1, 2, and 3. The next two rules is for a plane surface and a convex surface. If this surface is plane or the surface is convex, the view factor to itself is 0. The last is symmetry rule. If surface 2 and surface 3 is symmetric about surface 1, these two view factors are same. It indicates that if 50% of radiation heat flows from surface 1 to surface 2, the same percentage of radiation heat flow goes from surface 1 to 3 as well. B6. We use example 13-2 to show how to use the rules to find view factors. There's a long open channel with point B falling on the center of the line DC. It's a very simple statement. You may learn to add the implication, which is surface 1 and surface 2 are at a different temperature, T1 and T2. As a result, there's radiation heat transfer between these two surfaces. That's the reason we're interested in finding the view factors. Typically, the system is placed in a large surrounding at room temperature. Step 1. Since it is open channel, which is open system, we make enclosure by adding surface A3, which is surface BD, and 2 end surfaces at room temperature to represent the surroundings. Step 2. Since it is a long channel, the 2 end surfaces is so small, its contribution can be neglected. As a result, the enclosure is treated as a 2D geometry. We only care about radiation heat exchange between these 3 side surfaces, A1, A2, and A3. Step 3, since the 3 surfaces, each one has its own temperature, the total number of radiation surface N is 3. Step 4. If we check surface 1, it is plane, therefore its view factor is 0. Step 5. Since surface BC and surface BD is symmetric about surface DC, according to the symmetry rule, these 2 view factors are same. Step 6. This is 3 surface enclosure. We will apply summation rule. We let I equal 1, which we focus upon surface 1, and the summation rule states F11 plus F12 plus F13 equals 1. Next, we plug equation 1 and equation 2 into equation 3 to yield the view factor F12 value, which is 0.5. It makes sense because 50% goes to surface A3 and 50% goes to surface A2 from surface A1. Step 7. In order to find view factor F21, we will use reciprocity rule because we know F12 and surface area A1, A2, which are rectangular. Next, we'll plug into numbers. We arrange F12 to the left side of the equation, plug into A1, A2, and view factor F12 to get the view factor F21 value. At this point, we cover topic 1, focus upon the 3 important concepts, and topic 2 discussed the 3 methods to find the view factor value. See you next time.